Hello and welcome back to me answering questions from Robin Hartshorne's Algebraic Geometry. Today I will be answering question 2.4 of section 1. So let us begin. The first part of this question asks us to show that there is a inclusion reversing bijective correspondence between algebraic sets in P to the n and homogeneous radical ideals of S not equal to the irrelevant radical ideal. And Hartshorne already gives us very kindly the assignments we should be looking for, i.e. we want to show that I of VP of Y, other way round, so the vanishing set of the ideal generated by some algebraic set is equal to that algebraic set, and the ideal generated by the vanishing set of some homogeneous polynomial, some homogeneous radical ideal is equal to it. So, Hartshorne tells us that for any set of homogeneous polynomials, there exists a finite set of homogeneous polynomials f1 through to fr, such that the vanishing set of T is equal to the vanishing set of f1 through to fr, which in itself, verify this I guess, but it's a very simple fact, is equal to the vanishing set of the ideal generated by f1 through to fr. So, we can focus our... Oh, and also f1 through to fr are all homogeneous. We can focus our attention to the vanishing sets of homogeneous ideals. Now we want to split ourselves between two different cases. Firstly, assume that the vanishing set of our homogeneous ideal is not the empty set. Then, by 2.3d, the ideal generated by the vanishing set of I is equal to the square root of I, or the radical of I, which is not equal to S or S plus by, I believe, 2.2? Yes, 2.2. But we are discounting S plus. But for any algebraic set, we can assign to it its homogeneous radical ideal. Furthermore, we want to show that the vanishing set of this, so the vanishing set of the ideal generated by the vanishing set of I, is equal to the closure of the vanishing set of I, but this is Zariski closed anyway, is equal to I. Oh, and this equality is from 2.3 part E? Was it 2.3 E? Yes, E. I have my notes here. Therefore, for a algebraic set, Vp of I of y is equal to y. This is only half of the picture because we need to show that for a radical homogeneous ideal, we have I of Vp of I is equal to I, which we will show soon. But we should probably turn our attention to... Aha! No. Although, let's keep this. For all y subset of p to the n. Now we want to focus our attention to the other direction before we look at this. Next. Now we need let's see. I is a radical ideal which is contained within and not equal to the irrelevant radical ideal. In particular, the vanishing set of I is non-empty. Oh yeah, the vanishing set is non-empty. So by 2.3d, the ideal generated by the vanishing set is the radical of I, but as I is a radical ideal, it's equal to I. Thus, we have shown that minus the correspondence between the empty set and S, we have shown what we wanted to. Thus, let y equals S. By 2.2, this is equivalent to the vanishing set of S is empty. And then the ideal generated by the vanishing set of S is the ideal generated by a set. Let's call this set K, where K is all the homogeneous polynomials such that f of p equals 0 for all p in, oh wait, this is empty. Therefore this condition is never broken, therefore we can just ignore it. And the ideal generated by this is precisely S. And then if I is the empty set, then the ideal generated by the vanishing set of I is let me just Terribly sorry. Oh no. Well, the vanishing set is empty. The ideal generated by the vanishing set of S is S. And then the vanishing set of the ideal generated by the empty set is empty. Therefore, we have shown the bijective correspondence. Furthermore, well, not furthermore, the inclusion reversing requirement follows directly from 2.3a and 2.3b. Thus we are done with part A and can move on to part B, which is essentially an identical proof for the affine case with one major caveat, which is we need to add in an inductive argument. So, let y be an irreducible algebraic set, and let f times g be within its ideal. Now we rewrite f equals f0 plus f1 plus dot 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 all the way to fd, the degree d part of f. Or these are the unique forms which constitute f and g. G is g0 plus dot 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 plus g e. Therefore, given that f times g is within I of y, we have f0 g0 plus f1 g0 plus f0 g1 plus dot 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 plus fd times ge is within the ideal generated by y. Therefore, fd times ge is within the ideal generated by I of y as it is additively closed. Thus, y is a subset of the ideal generated by fd times ge, which means y is equal to which is the ideal generated by fd union ge. Vanishing set of fd union the vanishing set of ge, which is the ideal generated by fd intersect the ideal generated by GE. Let me just double check my notes to see if, aha, the vanishing set's not the ideal. I was thinking that it looked a little bit weird. The idea, yeah, bleh. So y is equal to the intersection of y with the vanishing set of fd union y intersect the vanishing set of GE. Therefore, we can continue because either y is equal to this or y is equal to this. There is just no getting around that because y is irreducible. Now, this means that y is a subset of the vanishing set of fd, or y is a subset of the vanishing set of GE. But that means that the ideal generated by y contains either the ideal generated by fd or the ideal generated by GE. This means either fd is within I of y or GE is within I of y. What this means is that as I of y is an ideal, we have not multiplied by GE, multiplied by G is within our ideal, or F multiplied by G minus GE is within our ideal. Ah yes, and this is the orientation reversing correspondence. Well, this is, I believe, 2.2.A is what I used there. But what this then means is that either fd minus 1 multiplied by GE is within I of y, or fd multiplied by GE minus 1 is within I of y. And we can do this argument all over again. So eventually we're going to run out of things because we have no degree minus 1 parts. Therefore, either all of f0 through to f1 through to dot 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 fd is within I of y, which implies that f is within I of y, or g0 through to ge is within I of y, implying that g is within I of y, and I of y is prime. Now let y be such that I of y is a prime ideal. Suppose y is reducible No, that's not what I've written in my notes. Suppose that y can be written as the union of two, well, you can just use y1 and y2. Suppose y can be written as the union of two algebraic sets. Then the ideal generated by y equals the ideal generated by y1 into two things. Union y2 equals I of y1 intersect I of y2. However, since I of y is prime, I of y equals I of y1, or I of y equals I of y2. This is just a fact about prime ideals. If a prime ideal is equal to the intersection of two other ideals, then it is equal to one of the or the other. Thus, either y equals y1 or y equals y2. This means that y is irreducible. By the definition of being irreducible. Thus, we are done, because we have shown that if this is true, then this is true, and then if this is true, then this is true. And we can move on to part C, which is very simple. The ideal generated by the projective n space is the ideal generated by the set K, where K equals f such that, well, homogeneous polynomials such that f of p equals 0 for all p in projective n space. What this actually means is we can just pull it into affine space. Well, this is nothing. And oh no, it isn't. It's 0. So the ideal generated by projective n space is 0, which is true if and only if we have an integral domain. Which is true, because this is a field, and the polynomials over a field are always an integral domain, and that's just a basic algebraic fact. Therefore, p to the n is irreducible, and we are done. And I can say, thank you for watching. Goodbye.